Thank you for the introduction. I will talk about, as already said, on parametric problems. So it connects very nicely to this discussion on affine problems that we heard on Dionysius. And just want to tell you from the beginning, I will mainly focus on structural dynamics, at least the examples that I present, but everything is rather methodological, so you can also apply it to vibroacoustics. And I also want to mention that this is joint work with Romain. So yes, this is. So just to keep the credits here. So let's take first a look at the motivation of the problem. So as I said, we look into some problems of structural dynamics, just here depicted as a beam. We discretize them with the finite element method, so we get this second order differential equation here. And as Dionysius also explained, we might end up with large matrices to solve if we want to go to a certain frequency that we want to investigate. So as we heard in all the previous talks, one solution to tackle this is to do model reduction. So we have smaller reduced matrices, and we can perform this frequency sweep or solving in many time steps more efficiently. However, as my title says, I'm looking into parametric problems, and actually I'm mainly looking into geometric parameters. So we could assume that the dimensions of this beam depend or are the parameters of our model. This of course translates to the system that we are solving. So all our matrices may depend on these parameters. And then for an efficient analysis in some multi-query context, such as an optimization, we don't want to do this projection every time we want to evaluate a new parameter point. Instead, we would like to have reduced matrices that also know about these parametric dependencies so that we can really efficiently evaluate them. So this will be the main goal of this talk, to find an approach that enables us to have these reduced matrices knowing about the parameter and allowing an efficient solution of the problem. So for that, I will first go into the mathematical system description. As I just say in the structural dynamics, it's rather simple, but just to make the notation clear. Then we'll go into this approach of parametric model reduction, namely matrix interpolation that I'm using. We'll then encounter some inconsistencies, so some challenges that are posed in this method. Then this will lead us to an adaptive sampling and clustering, which I will show you then, and finally the results for this approach. So starting with the mathematical system description. So as I said, we're looking into these second order systems. I'm looking into linear time invariant systems, so no frequency dependence here. All the parametric dependence is in, for example, geometric parameters. And it's already written in frequency domain, so we have this complex frequency S here, and then we have mass, damping, and stiffness matrices. The first equation gives us this equation of motion. I split the input into two parts, one frequency dependent part, so telling us the frequency content of the force that is applied, and one input vector F that gives us the location where this input is applied, so just telling us which degrees of freedom are excited. And then we have the second equation. Often we're not interested in the complete solution of our system, but just into one specific output. So we pick the quantities of interest with this output vector G from the whole solution in the frequency domain. And then you can write this down quite nicely as this transfer function. I'm sure you've seen this multiple times. So this just directly translates our input to the output, and it involves solving this dynamic stiffness matrix or inverting it for every frequency step. So this is where the computationally complexity comes from. So there we want to apply the projection-based model reduction. And it has been explained multiple times today, but I want to show it to you from a more geometric perspective. So for this, let's look at this beam with 3 degrees of freedom. If we do FEM, then this solution would be described by the sum of the nodal displacements. So we could imagine it as one point in this 3-dimensional space of the degrees of freedom. And the solution in frequency is then a trajectory in this 3-dimensional space. That is the full solution that we're looking for, but this is too expensive for us to describe it in the nodal displacements. So instead, we compute the reduced basis. So physically, we compute deflection shapes of our structure. So this could be the eigenmodes. And geometrically, this means that we span basis vectors, or we take basis vectors in this space, and they span a subspace. So you'll see these subspaces as announced by Romain multiple times today. So please keep this picture in mind. And when we do the projection-based model reduction, what we're trying to do is to approximate our actual solution in this space. And if the space is quite appropriate and accurate for describing our full solution, then we get a good result with a much smaller computational complexity because we're just in this reduced space. All right, so to revise this also from the mathematical point of view, we've seen this before. We want to describe our vector of degrees of freedom in terms of the reduced basis times the reduced vector of degrees of freedom. So this just gives us the participation of these deformation shapes to the total solution. And then this results in this projection. So first of all, what we can see here is that the structure of the problem is exactly the same. We still have this nice second order algebraic equation. The output equation is also the same. We just need to perform this projection to each of the full order quantities. And this can be done offline, as said before, and then we can do the frequency sweep. However, so far nothing is parametric, so let's also introduce the parameters here. And I consider the most general case that we just, or that all of these full order quantities may depend on the parameters. And specifically, it has been very nicely introduced by Dionysos, I'm not looking into these affine representations of the parametric dependency. So if you, for example, have material parameters, it can be quite easy to find a representation of a constant matrix multiplied with a scalar function of the parameter. Think about the Young's modulus in a linear elastic homogeneous material. It's just Young's modulus times the remaining part of the stiffness matrix. But if you're using geometric parameters, as I am, or maybe also other parameters, or if you have frequency dependency, then it's often not so easy to find this representation, or it might end up in a large number of constant matrices that you need to have a good approximation of this actual dependency. So I will completely ignore this and try to work with a method that does not require this dependency. And this leads me to the pMOR approach of matrix interpolation. This is one approach that does not require this representation. And first I want to introduce it to you. So just as an interesting side note, it was developed 16 years ago here at TUM actually. And it starts by sampling the parameter space. So for visualization purposes, let's just take a 2D space. We can place our samples in any method that we want, random, quasi-random, space filling, whatever you like. For each sample point, you compute the full order quantities. And then for each sample point, you individually perform the projection-based model reduction. So you compute a reduced basis for each sample point. I'll come to how to compute the reduced basis later. And then, as I explained before, you just do the standard projection-based model reduction for each of these individual samples. And then we can depict it with this sketch. So we have two samples, we have two reduced models. As the title says, we want to do matrix interpolation. So we want to interpolate the entries of the reduced matrices. And at this point, we can see that this doesn't make much sense here because both samples have been reduced individually, so they are not described in the same coordinate system. They are not aligned at this point. So we first need to perform a transformation of the underlying basis. So in the best case, we manage that they look alike, and then we can go on with the interpolation of the reduced matrices. So how do we do this transformation? I just quickly want to go through this. Still following this approach of Panzer et al. That was proposed here. So they proposed to take all the sampled reduced bases that we collected in the sampling into a large library and performing a singular value decomposition on that, because by this we can kind of get a ranking of the information that we have in this library and just take the first few, or the first R, left singular vectors as our generalized coordinate system, with R being the size that we used for each reduction for each sample point. So this should then represent our library of bases in the best way. And then we want to transform each of the sample bases to this generalized coordinate system. And if we are able to do so, then we can do a nice interpolation of the matrix entries. So we need to compute the transformation matrix, and let's start at the bottom. So our goal is to transform each sample reduced basis with this transformation matrix, so that this V tilde, the transformed basis, is similar to the generalized coordinate system. And they defined it as follows. They take the product of the generalized coordinate system with the samples and take the inverse. This automatically or explicitly fulfills or optimizes the modal assurance criterion. So it strongly fulfills that this product becomes the identity matrix. So corresponding vectors have a dot product of 1, they're identical, and non-corresponding vectors of a dot product of 0, so they are orthogonal. And with these transformation matrices, we can just apply them to the reduced matrices and have the transformed reduced matrices. So the nice thing about this approach is that we also don't need to store the full matrices after the sampling. We can just keep the reduced ones and only transform them to the same coordinate system. And then, if this worked out as nicely as it's depicted here, then they're described in the same coordinate system, and we can just fit an interpolation or regression model for the entries and directly predict the reduced system for any queried parameter point, which then of course is very efficient because we directly have a reduced system. We don't need to do any assembly or projection or anything else. But if it were this easy, then I wouldn't stand here and give another 20 minutes of talk. In fact, it's not that easy, and you can get what we call inconsistencies in the reduced spaces, which prevent you from applying this approach as straightforwardly as it was proposed initially. So for this, I want to go back to this geometric point of view. So let's say we have two reduced spaces that we sampled. So they're depicted in the same image here, but they are for two different sample points, so sample point I and sample point J. Then we have the two basis vectors that span these spaces each. And first we do this transformation, as I said. If we do this, then we would get probably the following transformed basis vectors. So we can see that these two subspaces have one common direction. So we are able to align one basis vector in these two subspaces to the same direction. But in this direction, the two subspaces differ. So the best we can get is having these two transformed basis vectors, which are not perfectly aligned, but just tell us the difference or the still closest match of these two bases to each other. Now the question is, can this become a problem? And unfortunately can. So let's think about what happens in the projection. So let's take one exemplary load vector. If you, for example, use geometric parameters, this input vector is usually constant because we don't change where this load is applied. So this usually doesn't have any dependency on the parameters. And now if we perform the projection of this load vector onto the subspaces, it would look as follows. So we project first on this first direction. We can see that this is identical for the two subspaces because we were able to align this one direction. So it's perfect. We keep this constant dependency also in the reduced space. But here, when we look at the second direction, just because the two basis vectors aren't aligned, the projected values, of course, may differ quite strongly. So in the end, we might have a parametric dependency in the transformed reduced quantities, even though there is no dependency in the actual full quantity, just because we have a change in the basis. So the question is, how can this basis change? What are the reasons for that? And how can we identify this? So coming first to the second point, how can we identify this? There's this nice concept of computing the subspace angles. So let's think about these subspaces again first. It doesn't matter if the basis vectors are transformed or not at this point. We can take the product of the two and compute the singular value composition of this. Then the subspace angles, so the angles between these two subspaces, are given as the Arcus cosine of our diagonal entries of the of the singular values. And this also gives us explicitly the directions where these subspace angles occur. So if we use this approach, then we could transform the reduced spaces with the left and right singular vectors, and they would tell us the first direction is perfectly aligned, as we already know. We would get an angle of 0 degrees between them, and the second subspace angle would be, I would say, roughly 45 degrees in this sketch, and we also know that it relates to this component and this component, which we get from multiplication with the left and the right singular vectors. So by this, we can probably use some heuristics. If this angle is very small between the subspaces, then probably there's not a problem in projecting them into different subspaces because the change is negligible. But if it's quite large, then probably we run into problems that they're depicted into different spaces, that they're projected into different spaces. So what are now the causes that these subspaces differ? And the first one is the model reduction method that we're using. And I want to depict this on this very simple example. It's just a beam that's clamped at one end. We apply vertical or load in z direction at the tip, and we also measure the displacement in z direction at the tip. Here it's depicted as a 3D model, but it's discretized just with 1D beam elements. We change the height of the beam, but just in a range that we always stay in the realm of Euler-Bernoulli beams, so just thin beams. The nice thing about this model is that when we change the height, we just affect the cross-sectional area and the moment of inertia. And if we look into the mechanics textbooks, we find out that the cross-sectional area is just affected linearly by the height and the moment of inertia just cubically. So we can capture the full model's dependency on this parameter with polynomials. So if we just did cubic spline interpolation, we can exactly interpolate the actual dependency. So if we get any error in our results, then it will be due to a change in the basis. So we can extract this here. So coming back to the model reduction methods, thanks also again for the introduction here, because I can spare some time here. The first one I want to look into is the POD. As it was explained before, it's very straightforward, rather simple from the concept. We just take some snapshot frequencies and compute the dynamic solution at these snapshot frequencies. And then we put them together to build the reduced basis. I want to compare this to modal truncation, which has also been explained multiple times today. So we take the undamped equation of motion here, and we compute or we solve this eigenvalue problem to get the eigenmodes, and then we just take a set of these eigenmodes as our reduced basis. Usually you take those with the smallest eigenfrequencies to have a good approximation in this low frequency regime. So I use these two approaches to perform the pMOR by matrix interpolation. And you can see the results on this slide. So the y-axis shows you the mean relative error. So I'm not showing here any transfer functions. I already condensed the error between the full and the reduced solution for each parameter point into one scalar value. And on the first glance, it seems as if POD works better than modal truncation because it gives a lower error in the whole range. But you can see that it's just very accurate at the sample points. And in between, the error increases quite drastically, sometimes up to 7 orders of magnitude. So obviously, there's a huge change that POD introduces into the reduced basis, because otherwise we would be able to exactly interpolate the parametric dependency with our cubic spline interpolation. Compared to that, if we use modal truncation, then we don't have this high accuracy with this reduced size at the sample points. This has also been discussed in length today, because we might have quite some modes that are not important for this problem. But we see that the interpolation error hardly increases between the sample points, so showing that we actually have a very nice match of all the reduced bases and can smoothly interpolate this actual dependency of our full quantities that we want to interpolate. So what is the exact reason behind that? And we look back to the POD. As I said before, we take the transfer function and we just compute the solution of that for some snapshot frequencies. So here I show the transfer function for the two bounds of the parameter space, one's 2 and one's 5 centimeters. And generally the dynamics of the beam don't change, they just shift in frequency. And if we use fixed frequencies as our snapshot frequencies, then once for the small height, so for a soft beam, we go up to the 5th mode of collecting information. If we take larger heights, then of course the eigenfrequencies increase. And if we go to the same snapshot frequencies, then we just collect information up to the 3rd or the 4th mode. So we have totally different pieces of information, once to maybe 5th mode, once to 4th mode. And therefore we introduce a huge change in the reduced basis that we cannot, or that will influence our total dependency and prevents that we have a nice interpolation of the reduced entries or the reduced quantities. Compared to that, if we use modal truncation, then we just take the eigenmodes. So here it's not depicted perfectly correct because we solve the undamped equation of motion, but just to give the picture, we always end up with the eigenmodes. And in this very academic example, they actually don't change at all because we still have this 1D example. It's Euler-Bernoulli beam theory. So we get the exact same eigenmodes every time. And therefore, we don't have any or introduce any dependency in the reduced basis and can fully capture the dependency of the actual full model. So we can actually solve this very nicely with modal truncation. But when we use modal truncation, we buy a new problem, which is mode switching and truncation. So for that, I'm using almost the same example. I just tilt the input by 45 degrees and the output. because if we do so, then we need to take bending modes in z direction and bending modes in y direction into account. Why is this important here? When we show or depict the eigenfrequency of these modes over the parameter, we can see that the eigenmodes or the bending modes in y direction are unaffected by this change in the height, whereas the bending modes in z direction, of course, increase their eigenfrequency if we increase the height, because the beam gets stiffer in this direction. And due to this, two modes change their position here, which is more or less just a coincidence. But it becomes a problem when we perform the reduction, because as I said before, we just take a subset of all the eigenmodes. Maybe we just take the first 4. Then in this case, you would have 2 bending modes in y direction and 2 in z. And for the larger heights, after the switching, if we take 4 modes, then there are 3 in y direction and 1 in z direction. So again, completely different information that we collect here. In the worst case, if we normalized our basis before, then these subspaces even become orthogonal. So you would get this picture for some parameter points until the switching occurs, we have the same subspace. Then we have the switching of the modes, and for all the remaining points, we have a completely different subspace. Again, for these sample points, the subspace is similar, but there's just this artificially introduced discontinuity in the reduced basis that we get here. So our solution to this problem is to partition the parameter space, so to approximately identify where this switching occurs, and then clustering all sample points to the left into one region, performing all the pMOR for these sample points separately, and then clustering the remaining points into another region, and then again performing all the pMOR for these points. So with this, we can also circumvent this problem of the mode switching. And there's just one more thing that we neglected so far, namely that the dynamics of the system may actually change. So far I just said we're looking into Euler Bernoulli. If we change the parameter, we still have the same eigenmodes. This is of course not the case for every system that we might look into. Oh, sorry, I forgot about the examples here. So just to show you, if we partition the parameter space, then again we have this very nice or smooth interpolation of our dependencies. We have the small errors. Here you can see that all the sample points that we used were clustered into 3 groups, indicated by the 3 different colors. And if we took the entire parameter space to build the parametric reduced model, we would get very high errors. Here the comparison is not totally fair because you run into numerical problems. If you want to do the transformation to the same coordinate system, if your subspaces are orthogonal, because then when computing this transformation matrix, you would have to invert the singular matrix, and then you just run into numerical problems, and this is why you also lose the accuracy at the sample point sometimes. So yeah, coming back to the last problem that we might have, the change in the system dynamics. So again, the same example, but now we change the height in a way that we transition from Euler-Bernoulli beam theory, so thin beams, to Timoshenko beam theory, so thick beams. And to show this, I depicted here the eigenfrequencies of the beam, and the color code shows the mean shear strain. So the more we increase the height, especially the higher eigenfrequencies, the more shear strain we have. So we transition here from the small heights, from pure bending modes to more shear modes. And then, of course, again, if we did a very coarse sampling in the parameter space of this problem, then we would also get large changes in the reduced spaces. So if you, for example, just sampled at 3 points, then it would seem as if there's a large change in the basis. But for this problem, the nice thing is that this transition is very smooth, as you can see here. So we just need a finer sampling, and then can also capture the change in the basis if we just adjust our sampling here. So this is shown in the final slide of this simple result section, or the result section on this simple example. If we use just 5 sample points, then we will get subspace angles of 20 degrees between the sample points, and you can see again that we have a huge increase in the error between the sample points because there's just such a strong change in the reduced basis that we cannot capture the actual dependency nicely. And if we increase the number of sample points, for example, up to 16, then we manage to have subspace angles of just 5 degrees between the sample points, or between the subspaces of the neighboring sample points, and especially in the middle of the parameter space, we can then very nicely still interpolate our dependency. And yeah, please note that here this increase in the error is really attributed again to the change of the basis, because the full model can be interpolated still accurately or quite accurately with the polynomials, even though we also have some shear contributions. But the main increase in this error is really attributed to the change in the reduced basis. So now we found 3 different causes that the subspaces might change quite drastically. We found a remedy for each of them. And this now brings me to this adaptive sampling clustering as a solution to bring these 3 individual remedies together. So for this, we developed the following approach. We start directly in the sampling, because before the transformation takes place, we need to make sure that we can actually transform all the reduced bases to one generalized coordinate system. So we start with a very coarse sampling, because as it says here, we want to do an adaptive sampling. So for that, we first perform a triangulation of the sample points. This is just done because we want to know which sampling points are neighboring to other sampling points, so that we can compute the relation to them, or at least the relation between the subspaces of these samples. So for each connection, so each edge in this triangulation, we compute the subspace angles, as I showed you before, and then we can give them labels. If the subspace angle is very large, so close to 90 degrees, we tag them as inconsistent, so that there is a huge change between the bases. If it's very small, maybe 10 degrees or smaller, then we would say it's consistent. And in between, we say it's unknown. It might be a problem of this change in the system dynamics. So if we place more samples there, we could make it consistent, but there could also be another problem that we don't know yet. So here, everything is inconsistent at this point. There, of course, we could stop and give up, but that's not the point here. So we also introduce some more criteria for the adaptive sampling, namely that we don't want to have too large distances between neighboring sampling points. So we set a threshold, let's say 20% of the distance of the parameter space. And then this adaptive sampling algorithm will just place more and more samples every time this distance criterion is not fulfilled, or we have a subspace angle with the label unknown. And this is how it would look like. In between, you can see that we get these edges with unknown consistency, and it places more and more samples until all the distance criteria are fulfilled and all connections are either consistent or inconsistent. Now we can nicely see that, for example, here we have 6 samples, which are all pairwise consistent with each other. So we can cluster them into one group, perform the pMOR just for these points, and then perform pMOR separately for all the points in the separate cluster. So just these labels in the connections directly give us the clustering, which you can see here. So as I said here, we cluster these samples into one, and then we perform the pMOR by matrix interpolation for each of these clusters separately. Now, finally getting to some results of this approach. So I'll directly go into a more complex one, Kelvin cell structural topology. So it's just a specific geometry that I think Lord Kelvin actually invented as some kind of attempt for space-filling geometry. It's discretized with beam elements, and we apply input or load on the left, we measure the output on the right, and we change the dimensions of this cell in x and y directions. We just stretch and compress it, so we have a 2D parameter space here. And actually, this example is just the one that I showed you before. So the adaptive sampling that you've just seen is the one that is applied here. So this is the clustering that you just saw. And on the right, you see the mean error, or the approximate H2 error, so the error in the area between the two transfer functions for 51 by 51 test points. You can see that this model performs very nicely actually for the whole parameter space. So in most regions we have errors below 1% or just in the range of a few percent. It can also be seen that for some clusters, this reduced size that we're using just provides more accurate results than in others. But in general, in most regions, it's very accurate. We just have an increase in the error mainly in the region between the two clusters. This is mainly because if we, for example, are at this point between two clusters, we somehow need to decide which pROM we should use. And here we're just using a very simple approach. We're using k-nearest neighbor classification. So we just take the nearest sample, and based on which cluster this belongs to, we take the corresponding p-ROM. So of course you can do more informed decisions, something more based on physics, which we're currently working on, but still with this approach, you actually get quite good results in this whole region. Then I also brought another example, which looks rather simple, but it's actually not that easy. So it's a plate with a hole, and the parameter is the diameter of this hole. And what makes it difficult is that the range of this diameter, it's varied from 20% of the height of the plate to 60%. So from a rather small hole to taking almost a whole space of this hole of this plate. And in these cases, you might want to change your mesh, because the hole just changes so strongly. You don't want to just distort all the elements. And this is not possible in the classical or in the initial approach of the pMOR by matrix interpolation, because you need to somehow compare the subspaces, you need to do the product of the bases. So what we did to solve this problem is to perform a morphing of all the meshes to a reference mesh, and then evaluating the reduced bases on this reference mesh so that they're all comparable to each other. And if we do so, then we can apply this to this problem. So as you see here, from 20 to 60% of the height, we change the diameter. And in the blue line, you see the accuracy of our pROM based on this adaptive sampling and clustering. So it divided all our sample points into 6 clusters here, so they can always piecewise interpolate the dependencies. And again, we have errors of below 1% in the whole region, in the whole parameter space. Compared to that, there have been other approaches developed that try to work or try to enable using the pMOR by matrix interpolation if the mesh changes, but they don't take the subspace angles into account. And again, here this comparison is a bit unfair because they just don't know about these large changes in the subspaces, so they will end up again in this 100% error, just numerical issues that they face, as we've seen before with the mode switching and the truncation. So with that, I want to come to my summary. I hope I made up the time that we lost on the way sometimes. So as I told you, we have, or the initial goal was to have this parametric reduced model. We encountered this challenge of inconsistencies in the reduced bases, and we found 3 causes for this. First, the model reduction method that we're using. Then, since we used modal truncation, we ended up with a problem of switching modes. And finally, we also saw that if the system dynamics change, this might cause trouble if we don't do the appropriate sampling. So for each of them, we found the remedy. I just explained them as well, using the modal truncation, then partitioning the parameter space when this mode switching occurs, and performing a final sampling, which were all combined to one general framework of this adaptive sampling and clustering to tackle all of them at once. And for an outlook, we're currently working on using this in an optimization. So now that we have this nice parametric reduced model, we of course also want to use it somehow. And one nice thing about this approach is that since we do an interpolation of the matrix entries, we know analytically the dependence of the reduced matrices on our parameters just by this interpolation model. So we can perform a sensitivity analysis, not only on the reduced matrices, but with that also on the response, like the output, and also on the objective function. So we can integrate this very nicely into a gradient-based optimization. And since I've just been talking about structures and no acoustics, of course, the application to vibroacoustic problems is something that we also should do once with this approach, because we heard today modal methods are also frequently used in vibroacoustics, so there's probably a very nice connection of these approaches here. So finally, just want to show you my references, especially if you're interested in this adaptive sampling and clustering algorithm. You can find it here. And the one on the varying meshes is just available as a preprint so far. Hopefully it will be read by the reviewers sometime. So with that, I want to thank you for your attention, and I'd be happy to answer any questions that you have on this talk. Thank you so much.